Hi everyone, it's Phil from My Math Teacher is Terrible. Thanks for joining today. As the title suggests, I have a probability problem today. But it is a physical probability problem. That is, it's a probability problem that involves geometry. So we'll kind of like pull from sort of two bodies of knowledge in order to solve this one effectively. We'll see what happens. There are a few interesting things that happen along the way, and I hope you find them interesting as well. I think this is a super interesting problem. I didn't write the problem down. I'll just dictate it because my handwriting is about as terrible as your math teacher is. So the problem is this. There is a dartboard, which is circular, and we have a square inscribed inside the circle. What is the probability of hitting the regions that are between the square and the edge of the circle? Super interesting idea. We can look at things like kind of a normal dartboard where we have like those sort of like pie slices and figure out some probabilities of getting the dart here or there. But this one is kind of interesting. And that's all the information I have. I know that I have a square inscribed in a circle. I have a circle. And I just want to know the probability of getting a dart, throwing a dart in between the edge of the square and the edge of the circle. All right. So, as you've checked out probably in some of my other videos, what do I do with geometry problems specifically? The first thing is always draw a diagram. Because geometry, right? It's the visual practice of mathematics, or one of them anyway, and that's a really great place to start. It helps to orient us toward the problem, and then also helps us point in a direction toward the solution, we hope. We can point in any direction. Sometimes we'll go to a dead end and then come back. That's also fine. And again, that's problem solving. And as you do more problems and you gain more experience, you gain that mathematical and problem solving intuition that we're kind of all after. That's like that's the place everybody wants to be after pursuing math problem after math problem after math problem and sitting through terrible math teacher after terrible math teacher. Okay, the diagram. We have a circle. It's going to be a terribly drawn circle, I promise you. Right? Actually, not too bad. Okay, I have a circle, and then inside the circle, I have a square. Let's do something fancy with another color. This is where you'll see just how terrible this circle is, but that's okay. This is just a guide for us. That's the other thing, is we are just making an approximate diagram. Ooh, a very, very terrible, very rough approximate diagram. I'm going to erase this, and we're going to come back to a nicer diagram through the magic of editing. And we've done a much better job. How nice. I can't remember how long that actually took me to do, but here is our diagram, okay? We have a circle on the outside, and we have a circle inscribed inside. So inscribed means inside. Circumscribed means outside. I could also draw a square outside of this circle, but that's not what this problem is telling us. Okay, cool. All right, so the first thing I do when I'm doing a geometry problem is draw a picture. Yes, and I managed to do that without wasting the rest of my afternoon. Okay, then the second thing I do is mark up the diagram with stuff that I know, right? Okay, so what's some stuff that we know? Well, we know we have a square. So what do I know about squares? I certainly know that all the sides are equal, right? I know that. And I also know that I have some right angles in here, right? Every square, 4 right angles, 4 equal sides. What do I know about the circle? Not much. But we do know that the basic defining characteristic of the circle, well, there's 2 of them. 1, where's the center? And 2, the radius. Those are the 2 things that we know about the circle. So let's, in blue, I guess, because that's what color the circle is, let's draw the center of the circle, and let's draw the radius. But let's draw a particular radius, okay? Let's draw one that actually intersects the square at a corner. And to make it a little bit more convenient, I am actually going to erase this right angle mark. If all 3 of these are right angles and I have equal sides, there's no choice but to make this a right angle geometrically when you draw it. Probably a lot better than this, but that's fine. Okay, so I'm going to draw the radius of the circle to the corner. Notice that drawing the radius through one of the sides may not help us. I've solved this problem already. I can tell you it does not help us, for sure. But okay, this is all I know. Nobody told me the side lengths. Nobody told me the length of the radius. Nobody told me anything like that. So I feel like I'm missing a bunch of information, right? And I am. And this is one of those problems where, like I do this with my SAT students in particular, where they look at a problem and there appears to not be enough information, and I call it a like just push through sort of problems, because some interesting things will happen as a result of pushing through. All right. So let's now write some things that maybe we know, but we're not sure what to do with. Right? Let's talk about some lengths of things. Let's talk about the lengths of the sides of the square, and let's label them in a way that we can do some computations on them. Right? Let's call the side of the square's length S for the side of the square. And also appropriately, let's call the radius of the circle R. Okay? And that's about as marked up as this diagram's going to get, for sure. Those are all the defining characteristics. All four sides will be labeled S, but it turns out I just need one of the sides, and you'll see why. Okay, and now let's just revisit or just talk more specifically about the probability portion of this problem. Okay? And remember that the probability of anything, in black, probability is defined as a particular event over the total number of ways or the total number of events. Right? And this is just a fancy way to say add them all up. Right? For those who don't know this material, it's just like I can also say this is one outcome, COME, over all outcomes. Right? When you flip a coin toss, getting heads is 1 out of 2. All the outcomes, there's 2 outcomes on the bottom, right? The bottom is all the outcomes. 1 out of 2, heads or tails. There's 2 possibilities. And to get one of them, it's actually 1, right? It's 1/2. So it's that kind of thing. When you're throwing a single die, 6-sided, normal one that you see in Vegas or on a board game, if it's got 6 sides numbered 1 through 6, the chance of getting any number is 1/6, right? 6 on the bottom is the total number of sides that it has, or total number of possibilities. And then there are 6 of each number, but getting any one of them is 1 out of all 6 of them. That's really what this is. So, fine. So we're talking about the probability of getting the dart in this area. So here we're going to think of the circle. If the dart lands in the circle, that's fine. I mean, the dart could land outside of the circle, but I'm not concerned with it landing outside of the circle. So really, all the possibilities, the total possibilities, is going to actually be the circle itself. That's the 100%. That's all outcomes, is the circle. Right? Because if I hit it here, I'm inside the circle. If I hit it here, I'm inside the circle. If I get it in the center, I'm inside the circle. Even if I get it on the circumference, I'm on the circle or in the circle. But if I get it out here, I actually don't care in this problem. Okay, so I want to know the probability of getting a dart in this area here. Okay, so now I've actually positioned this problem. I don't want to draw through my S. I've positioned this now as some sort of thing out of the total, right? So the area that I shaded, I don't want it in the square. I want it here. So now we've got to figure out what proportion of the shaded part, what the ratio of the shaded part to the total is. Okay, and we're talking about areas. Okay, so let's erase this. I'll come back to this when we get to the probability portion, but this is just a review of what probability is, just so we can start thinking about it. So we want to know the portion, or one outcome, to the total, which is the circle itself. And we're going to think of it in terms of areas of these things. Okay, so immediately when I said area, we can like cook up some stuff. Right, so let's call the circle C. So the area of circle C, right, we know that. Right, it's pi r squared. I don't know r. Okay, but that is the formula for the area of the circle. That's the 100% part. Okay, and then the formula of area of a square. I'll just maybe say area of a square here. Area of the square is s squared. It's s times s, right? Base times height, it's a quadrilateral. Or for square, s times s, which is s squared. Okay, great. So now I want to find out how I can calculate, and I have no numbers. I'm going to have to do this all in symbols, but again, something interesting is going to happen. I have to figure out what the probability of getting it in the shaded area is. So let's say area capital S. The shaded area is the area of the circle minus the area of the square, right? Right, this is shape math. Like suppose I was making a donut or something out of a piece of dough and I wanted a square hole in the donut, right? That's pretty much what I'm doing. I have the total circle, the filled in circle, the entire area of the circle, but then I want to cut the square out of it. Right, so the shaded area, this capital S is the shaded area here. I'll call this capital S. All right. Okay, and now going back to our probability definition of the event or the smaller portion out of the total. The smaller portion is going to be S, and the total is the area of the circle. So if I say that the probability of getting the dart in capital S, it is over the total is going to be the area of the circle. And the part that's not in the circle is going to be the square. So it's going to be the shaded area over the total. So it's going to be area of the circle minus area of the square. Right? This is the part over the total. The total is the area of the circle. The part is the circle minus the area of the square. And that is the probability of getting a dart in the shaded area. This is the proper notation for that. The earlier notation I did was just a little shorthand while I was talking about it, but this really is the actual notation. Okay, and sure, let's see what happens by just plugging in what we know so far. Let's see what happens. Okay, so I'm going to continue. Everywhere I see area of the circle, I'm going to put pi r squared. Fair enough. And everywhere I see the area of the square, I'm going to put s squared. Right? I'm just going to substitute these into here. Fair enough. Minus s squared. And then over the total, area of the circle, again, pi r squared. All right. Again, I don't know r and I don't know s. How the heck do we find out what the radius is? The radius is the one, because I'm not sure what to do here. I really would like everything to be either in terms of s, the side of the square, or everything to be in terms of the radius. And if we think about the geometry of a square, I'll do it over here. Let's talk about that. Let me do it in a different color. We'll just do green. We'll just say, let's talk about the geometry of the square. And this is strictly a geometry problem. Right, here's a square. All the sides are equal. I'm not going to mark up the right angles. I just need one of them if all these sides are equal. Prove it to yourself. Okay, and we're saying that my radius is here. But really, actually I want to mark this guy up as a right angle to stay out of my way when I do the next step. But what are we saying? Here's r, right? All I did was reproduce this. All I did was reproduce this diagram. But if I extend this, I might be able to do something, right? What do I know about this? So I know that I have a right angle, and then with the diagonal extended through the center here, I actually have a right triangle. And not only do I have a right triangle, I have a what? I have a special right triangle. I know that I know something about the angles in here. I know that this angle is 45 degrees. And of course, this angle is also 45 degrees because the sides are equal. It's an isosceles right triangle. And remember, these guys are the base angles in here, the 45s. They have to add up to 90 because I already have a 90-degree angle here. The area of this triangle here adds up to, the angles in this triangle here have to add up to 180. 90 plus 45 is 180. Now let's revisit what we know about special right triangles. So if I have a 45, 45, 90 triangle, or an isosceles right triangle, Pythagorean theorem tells us what? This is the hypotenuse, right? I'll call this C, not to be confused with that C. This is different. This is just the hypotenuse, because when I write a squared plus b squared equals c squared, that's that C. Right? Right triangle, and our buddy, the Pythagorean theorem. Okay, but S is A and B. S squared plus S squared equals C squared. Okay, S squared and S squared, those are like terms, so 2S squared equals C squared. And then here, I need to get what's the value of C. So I need to take the square root of both sides. So let's do that. And I get that C is, this I can split up using the rules of roots and powers. This is the square root of 2 times the square root of S squared. Let me just write it like that. And then here, the square and the square root cancel. So I know that the hypotenuse is square root of 2 times S. Great. So I know that this entire length is this. But I'm interested in R. What is R? Or how long is it specifically? Well, R to the center of the circle from the corner is half the length of the diagonal, right? So once I know this, I can easily say the bit of information that I want, little r, that R equals square root of square root of 2, my bad, is square root of 2 is root 2 times S over 2. Right? To take half of anything is to divide it by 2. And now, what do I have here? I have R in terms of S, which means anytime I see R in here, I can substitute this. But can we do something easier? Because I don't feel like I want to square this stuff. Maybe I want S in terms of R. Let's just see what that looks like. So if I wanted to solve for S here, I actually don't feel like I don't feel like I want to do that either. It's going to be a mess because, well, not a mess, nothing that we can't solve. I just don't like these fractions. I mean, there's just nothing I could do about that. So, okay, let's just go back to this, and now we have something for R. But let's make this a little bit easier on ourselves. And it's a good time to talk about how we deal with fractions. I see that these things are the same. I sure would like to cancel them out to make my life a little bit easier. But I cannot cancel them like this. I have to actually split this fraction apart. Right? Let's just take another sidebar and say 5 plus 6 over 7 is 5 over 7 plus 6 over 7. I have to split this fraction apart across the plus sign. I see that I want to cancel these, and man, if I split this fraction apart like this kind of thing, something plus something over 7 is something over 7 plus the other something over 7. I'm going to split this apart because I'm going to make my life a lot easier. I don't feel like squaring this a bunch of times. And this is where like a little bit of insight or intuition and experience comes in. Great. So let's take advantage of that. So down here I have pi r squared over pi r squared. minus s squared over pi r squared. Okay, all I did was split apart the fraction just like I did here. Great. I'm going to erase this junk so we can keep our problem solution clean. Okay, so now I have something cool. Something over itself is 1. All right, so now I just have equals, and this is the probability. I'm still marching through calculating the probability. It's 1 minus s squared over pi r squared. Okay, great. And actually this makes sense. Remember that probabilities can be no bigger than 1. The definition of probability of some event is between 0 and 1, where 0 is impossible and 1 is certain. And that's exactly what we have here. I start off with something certain, getting it in the entire circle, because I'm only concerned about the circle. Inside the circle is certainty, minus the part of the square that's, minus the square that's pulled out of the circle. So it actually is going to be less than 1. If I got it in the circle, 100%, right? If I get it anywhere in here or on the edge, that's 100%. So right away, this is telling me, yeah, this looks like I'm going to go 100% minus some stuff. And I'm going to get this shaded area that I'm after. This is the key insight, I think, in this problem, is that we can actually write out the radius in terms of the side length. And again, look, I have no numbers here. I've not plugged in any numbers except for this square root of 2 thing. And we know this about 45, 45, 90 right triangles. I think you find that out in geometry, and then you also, I think, use it in algebra 2. But these are the only numbers that I've introduced. A half, because I know it's half of the diagonal, and then the length of the diagonal always is the square root of 2 times one of the sides. Okay, I am actually going to erase this, and we're going to continue our probability calculations up here. So I'm going to leave the green part because I'm going to need that for a second. Let's just hang on to that. I'm not going to forget it, but let's continue here. So we know, and this is where something super interesting happens, and you'll see. Okay, so we're going to continue up here. So again, my probability of getting it in the big, of getting it in capital S, the shaded region, is 1 minus s squared over pi r squared. And now is the part where I have to do this. I have to put this in for r. All right, let's do it. Equals, so it's 1 minus s squared, and then the bottom is going to be pi times r, so it's going to be this whole thing. Square root of 2 times s over 2 squared. This is r, right? So all I did was just straight substitution. This looks messy, man, for sure. It looks totally messy, but I promise you it'll clean right up. Okay, what can we do with this? I can do something, can I do something slick here? I'm not quite sure I can. So let's just go through and square this whole thing and then see what happens. Okay, so 1, I can do something slick, but it's going to maybe look confusing. Okay, s squared stays on the top. I have pi here. What does this whole thing squared look like? The properties of squaring a fraction means you square the top and you square the bottom. Okay, let's square the bottom first. 2 squared. Not bad. And the top, I'm going to square root of 2 times s. And when I square an expression like this, I square this and I square this. The square root of 2 times the square root of 2 is nice because we undo it. It's 2. And then s squared, well, it is a s squared. Not so bad. Okay? Now, before we continue, this is a compound fraction, but it's not so bad. Let's do one thing before we continue. We can actually deal with 2 over 4, right? Because I'm multiplying. This is different than this. If I'm multiplying, I can cancel. If I'm adding or subtracting, I cannot cancel. So this actually comes up in this video, which is super interesting. Here, I cannot cancel these until I pull the fraction apart. But here, I don't have anything to pull apart because I'm multiplying. So 2 over 4, that gives me 1/2. And to save space, I'm just going to reduce it right in place. Okay, so I'm going to have, I'm going to have 1 on the top, which just leaves the top as s squared. And then, of course, 2 on the bottom for half. Okay. This fraction still is a little messy, but that's all right. We know, and actually, I don't need these parentheses anymore to save space. Pi times this is pi over 1 times this, which means I can move the pi to the numerator here. So this is going to be pi s squared over 2. So let's do that. It's going to be pi times s squared over 2, and it's s squared over that. Now remember, we're going to do what we do with fractions over fractions, and that is keep, flip, switch. Right? We're going to keep the first guy, minus. Maybe let me make some more room for this. It's going to be big. And this, I'm going to erase this down here because we've already used it. Okay. So now I'm going to do 1. Now I'm going to keep the top. And then I'm going to flip the bottom, right? I'm going to make it 2 over pi s squared. And then change dividing to multiplying. Okay? And then in order to multiply this, I just put this guy over 1. Okay. And now when we multiply things, they're just going to kind of wind up together in the top and in the bottom. So this is 2s squared on the top because I multiply straight across the top, straight across the bottom, like this. And to save space, I'm just going to erase it and replace it with what it turns out to be. Okay, so this is s squared times 2. I would like to call that 2s squared. And then on the bottom, it's 1 times this, which is just this, right? 1 times anything is itself. So 2s squared over pi s squared is what it turns out to be. Let's put that in here. It's just room to save room. 2s squared over pi s squared. And again, what can I do here? I have s squared over s squared. I'm multiplying here. So I actually can cancel those. That is not the same as this because I have a minus sign. When I have a plus sign here, same thing. I have to pull them apart. But here, I can cancel them. And that's the super interesting bit. Because now I have no variables at all in this problem. I went from having 2 things that I didn't feel I knew, and how the heck am I going to calculate the part over the total to get the probability? But, again, I think I called it a just push through it problem. This is totally a just push through it problem. Because as I push through it, step by step, all the variables drop out, which is crazy. So this turns out to be 1 minus 2 over pi. No variables. So no matter how big this square is and how big this circle is, right, the circle could be the broadside of a barn, which your friend can't hit when they have too much to drink and play darts. But actually it could be. So here we go. We just have a number which says no matter what the size of the circle is, and of course the size of the square is going to change in a similar scale to the size of the circle in order to be inscribed inside of it. And then let's use some approximation. What do we know? We know that pi is approximately 3.1415927. Right? I memorized that. I think it's 27. I think the 7 I'm not so sure about. But anyway, we can really say that this is approximately 3. So if I say that this is approximately 3, I can actually approximate what this is. Now I'm going to do the squiggly equal signs. It's going to be 1 minus 2/3, which is, now this part is equal to 1/3. So the probability of getting it in the shaded area is approximately 1/3, regardless of the size of the circle and the size of the square and all that sort of stuff. And we just have to remember that the size of the square in the circle is going to scale with the circle. There's no way I could scale the circle up and have a different size square proportionally, because the square has to have 4 points that are on the circle. prove it to yourself that if I make it really small, these points have to travel inward and be on the circle. It changes the problem if the points are no longer on the circle. But I can scale it up and down. All squares are similar to each other, right? Because they all have 4 equal sides and 4 right angles. So I scale it up and scale it down. All squares are similar to each other. That's something special about squares. When you see a square, you're like, boom, that's a square. If it's a window, if it's a chessboard, you recognize it because all squares are similar. And actually, all circles are similar. Because the only thing that changes is the radius. And we can apply a scale factor to the radius, and we get a circle again. We can sometimes get a smaller one or a bigger one. So the geometry of the square and the circle, the geometry of a square being inscribed in a circle is intimate to this problem. Like it works at any scale. And the scale factor makes the circle bigger, but the probability does not change. That's what this says. Like, we really said when we got down to here, we said that the probability does not depend on the dimensions of the circle, which is usually just the radius, and it does not depend on the dimensions of the square, which is little s. They're not in this answer at all. They just totally dropped out. I find that super interesting. And we draw a box around this, a very terrible box because I didn't bend down a little bit. But that is the answer. We're done. It's approximately 1/3. I find that very, very interesting. And again, we had 2 things that we had no idea what we're going to do with them. Pi is a number, so we know that. But then after that, we actually just pushed through, and we see that all the variables eventually dropped out of this problem. And we get that the answer is approximately 1/3. All right, and that's it. What more do we do? That's it. We got the answer. We drew the box. We're ready to move on with our lives. But yeah, that's really it. So thanks for joining today. I find this problem very, very interesting, that it actually is a consistent number regardless of the dimensions of the problem. And this is a really, really great example of a physical probability problem, specifically one where we have some sort of geometric thing, and that we can reason always about probability as the part divided by the whole, or the total. And that's really what we have here. The area of the circle is the total. The top, the part that we want is just some shape math. It's the area of the circle minus the area of the square gives us the shaded part. That's all. Great. Well, thanks for joining. I really appreciate it. I've been a little sluggish with videos lately, but I promise to try to do some more. I have a couple calculus ones in mind, and then I also have some other ones where maybe I'm thinking about doing a series on how to use Desmos, which is like my favorite math tool probably ever at this point. There's some really great ones out there, but that one is great, and it's free, and it's super useful. So just kind of stay tuned to my channel for that. And yeah, just keep checking back. Again, thanks for joining. I hope you learned something. And please ask any follow-up questions you have, or make any comments you like in the comments section. You can follow me on Instagram, subscribe to my channel, and let's keep on going. All right, well, thanks very much, and I hope to see all of you soon. Thanks.